Good morning, everybody, and welcome back to Next Door NetAdmin. Last week, we talked a little bit, or I talked a little bit, about ROMs and how we've gone from a straight ROM with read-only memory to programmable read-only memory, or PROMs, and how we've moved on to EPROMs and EPROMs, electrically erasable, well, first erasable with ultraviolet light, and then electrically erasable, and how that's led us into flash memory. What all of those have in common is that they are about memory. It's in the name. So this is very much reprogrammable static memory. But what if we looked at this from a different perspective altogether? Because with this memory, you're always needing a processor of some sort to execute the instructions in that memory. What if we had something that we could reprogram specialized processors on the fly? And what would that look like? There are very common specific processors that are developed for specific needs. Typically, these are called ASICs. Application-specific integrated circuits. And you see them in a lot of specialized applications. For example, on a switch or a router, you'll have a general-purpose CPU, absolutely. But it would be extremely slow and subject to latency if every single packet through the router or every single frame through the switch had to go through the CPU. And as a NetAdmin, you want to avoid that as much as possible. It slows everything down. It adds latency. Because of that, the logic for line switching, as long as you don't have to hit the CPU for NAT, or for custom policies, for routing or anything like that, as long as you don't need the power of the general purpose CPU, the actual switching and routing can be done by ASICs. And a switch will have many of them. An inbound frame arrives. If it's doing cut-through switching, for example, it will just read the frame until it decodes the destination address, and then it will shunt the whole thing right through. Just like that. An ASIC has enough logic to look up in the TCAM of the switch which port has this destination address, and then connect the necessary data lines to send it to the outbound port. And that ASIC has enough logic to receive the inbound frame into a buffer or a queue and then send it out on the line in sequence. Cool. All of that is done at high speed. It just happens at speed because it doesn't have to go into the main CPU. It doesn't have to deal with having data in registers. It doesn't have to deal with being fetched into memory and then read from memory. None of that needs to happen. The ASICs have just enough logic to do the task that is necessary and no more. Anything beyond that does have to go to the CPU. Any of your command shells or other, administrative niceties happen through the general CPU. But that way you don't need a very powerful or several very powerful CPUs. You need one CPU for management, mostly, and for other high-level necessities. And then you have a bunch of ASICs actually handling the traffic through the switch. And this is no different in other industries and other applications as well. You can get very application-specific integrated circuits, that's what they are, and you can have those in your hardware in order to perform specific tasks. Now, just like with ROM, that's great, but what if you need to replace it? And this is even trickier than ROM, because ROM typically, comes with, a package, possibly, if it's not directly soldered on the motherboard, you might have a socket that you can extract the ROM chip from and put in a new piece of hardware with your newly encoded memory. Or in the case of an ASIC, typically speaking, while theoretically, I guess you could do the same thing and put in a new version of your integrated circuit, typically you won't do that. ASICs are even less replaceable, I would say, than most ROM chips that can be designed for replacement. So, not very replaceable at all. So, how do we do that? Well, it's trickier than it is with these types of read-only memory. Because, and again, I'll preface this by saying I am not a hardware engineer, so I'm going to be talking about this from my understanding, which is that of a network administrator who likes to read and learn about things, but I don't actually develop hardware, so bear with me if I am inaccurate in some of these details. But for the memory that we were talking about last week, it's basically storing a charge in a floating gate, so that as you run a low amount of current, the charge that is stored in the floating gate will impact the signal that's being run through it. And you can measure that impact to determine whether it's a 0, there was no impact because there is no charge, or a 1, there is a charge and it's influencing what I'm getting back when I try to run current through the line. But for logic, or an integrated circuit that's doing some sort of processing, some sort of logic circuit, it's a very different thing. And it's somewhat more challenging because you're not just storing a charge. You're actually having to reconfigure the hardware to say, I want it to go through this type of AND gate, I want it to go through this type of OR gate, I want it to go through this NOR gate, I want it to go through this XOR gate. Lots of different, or a NAND gate, or a NOR gate, or all the other types. And yeah, the logic stuff can get really complex, but just so you have an idea what we're talking about, an AND gate takes 2 signals, and all of these take 2 signals in and put 1 signal out. An AND gate outputs a signal if both inputs have a signal. And that's it. An OR gate puts out a signal if either one of the inputs, or both, have a signal. An XOR gate will put out a signal as long as there's one and only one of its inputs that has a signal, but it could be either one. And we just go through and build up these sorts of logic applications out of these building blocks. So typically speaking, that the way these work is that there will be a whole bunch of AND gates, a whole bunch of OR gates, all the gates that you need, and how you're programming it is you're instructing the device to connect or disconnect those signal lines in the correct places so that everything flows together in the way that you want. This is time-consuming, this is complex. When you're doing this through lithography by actually creating a burned-in chip or an ASIC, you can optimize this to some degree. And for the reprogrammable versions, not so much. These reprogrammable versions, incidentally, are called FPGAs, typically speaking. Programmable Grid Array. You can also see them referred to as PLAs, Programmable Logic Arrays. That's a little broader. And what you'll actually typically see these days is FPGAs, which means Field Programmable Gate Arrays. They're meant to be reprogrammed out in the field, not just in a factory under specific conditions. You can think of this as the difference between a PROM, programmable read-only memory. It requires special equipment. It's probably only done in the factory. Versus EEPROMs, which are electrically erasable. You find them in the field all the time, and you can reflash them whenever you want. FPGAs, then, are your equivalent of the EEPROMs. They can be field programmed and field reprogrammed, but they have their disadvantages as well. A reprogrammable variation, that is, somewhat expensive, comparatively speaking. The benefit is that it makes it easy to replace the programming. However, these are also not typically, they're typically, once you program them, cool, they usually have a bit of static RAM, static memory, where they will save the information. But the routing is also very complex on the chip. Because when you think about, okay, I've got a whole bunch of AND gates. What if I need to get a signal from an AND gate all the way to where the OR gates are on the chip? Okay, you're going to have to deal with some complex routing there. Versus if you're just burning it into the chip, you can just put an OR gate right by the AND gate, and that's cool. They don't have to be on physically separate portions of the chip. Or alternately, you don't have to have a mosaic where it's, I'm going to, just to make sure I always have something handy, I'm going to put an AND, OR, and a NOT, an AND, OR, and a NOT, an AND, OR, and a NOT. Well, what if you need a few ANDs? Well, now you're having to link these spread out, slightly spaced AND gates, and then maybe you want a NOT gate, and then you want an OR gate. The routing can get complex. So these FPGAs, in trying to get something that actually works reasonably well, they can be more complex. Their benefit is in their reprogrammability. You can get ASIC-like performance from something that is reprogrammable on the fly, essentially. And so you'll often see these used for prototyping, because that makes all the sense in the world. Use something that's reprogrammable to figure out what you actually need a hardware version to do, and then you can take that design and actually make proper ASICs out of it that are fixed and don't need to be reprogrammed, because that'll be cheaper for mass deployment and easier for people to deal with, because they don't need the static RAM to contain the instructions of how to do all of this routing and how to, join which connections in which order in order to form what you need. There's something else, though. Sometimes you might see, you'll probably see ASICs on a server somewhere, but given that they're not reprogrammable, nobody really worries about them that much. You might see FPGAs in a server environment, but again, very specifically around prototyping and other very specialized applications where you need the reprogrammability, but complexity is the cost that you're willing to bear for that. But there's another type of circuit that you will see from time to time in a server. It's something that I have mentioned before very briefly in previous videos about updating firmware on Dell servers, as it was at the time, and that is a CPLD. The CPLD is a complex programmable logic device. And that means, yes, it is a type of PLA. It is a programmable logic array. Where it differs from the FPGA is that a CPLD is not, it's a complex programmable logic device, but it is not as complex as an FPGA. And once it's programmed, it stays that way. It doesn't require a whole bunch of information on what connections to it just stays the way that it is. And it's a logic gate. It's a logic device, which means it's not running a program. It's not running any sort of instructions. It's just handling logic in a reprogrammable way. That means they're also typically smaller. They're less capable than an FPGA. One of their biggest advantages, however, is the fact that they are essentially instant on. Because they don't need to load a set of instructions, they don't need to load a list of which connections should be connected or how everything should be routed. They're immediately instant on. And in a server, they'll handle some tasks such as when power is connected, which components get power in which order. It goes through a voltage regulator. Probably. Most of them do. What do we do if the voltage regulator is not responding? Or what if it's outputting power that is not to spec where it should be? If it's not within that spec, don't send power to the CPU. If it's not within spec, don't send power to other things. In the newest Dell servers, apparently, the CPLD also handles the power sequencing for the networking cards, which makes all the sense in the world. You want to make sure that these components get good, clean power. That also means that once this sort of instant-on power-up logic is in place, there's other components that then come into the mix. You'll have a baseboard management controller, or BMC. If you have lights-out management, with the integrated lights out that HP servers have, or the integrated Dell remote access console, or iDRAC for Dell servers, or IPMI in general, then those processors can begin to load their operating system and begin to provide an environment for management. The main CPU can be turned on and begin looking at system RAM and testing all of the other components in the server as part of power on self-test. The CPLD is what handles all of the initial logic to allow all of those other components to start up. So it doesn't have a program. It has no applications running whatsoever. It's just logic. But it's also logic that can be reprogrammed. So if Dell, let's say, has sent out a bunch of servers into the field and they find out that, when we were developing this, we had, very stable power and everything's essentially under laboratory conditions. But out in the field, we're seeing that the variance in power at customer sites is leading to a failure condition for this 20% of machinery. You can reprogram that initial logic to handle those conditions. You can reprogram that instant on startup logic to take account for varying conditions, or to say, you know what, maybe implement an additional delay to give power time to stabilize before you pass the power through to the next component in the cycle. There's a lot of things that you can do, and there is a good reason for having a CPLD in there for that sort of foundational task. Comes with its own caveats, of course, because this is the very foundational logic for just plugging something in before anything else even starts powering up. The CPLD is, at least in Dell servers, I don't know too much about HP servers or the other types, but at least in Dell servers, I can say for a fact, CPLD updates are the only thing that you can install. You cannot install anything at the same time. And when you do install a CPLD update, it does knock the entire server offline, even the management card, because you're busy updating something that handles the foundational logic before the management card can even turn on and start providing you that remote management capability. that means that the CPLD is one of the two components in the server that kind of makes me sweat when I need to update it. The other one being the power supplies, because hey, if your power supply firmware update doesn't work, then you've got a bricked power supply. Same thing with CPLD. If something happens during a CPLD update, your server's not turning on again. Period. It can't, because that logic that provides power to the other components isn't there, or it's there in an incorrect fashion that doesn't allow everything else to work. So even though CPLD updates are necessary, you want to resolve those bugs. You want to make sure that you have fixes and updated logic that matches what is being seen in the actual field. But it's something that's going to make me sweat every single time. So, yeah, it's not something that you do casually, but it is something that has very good reasons for needing to be done. So there we go. We've discussed ASICs, FPGAs, and CPLDs, all the logic variants of what we saw in memory last week: ROMs, PROMs, EEPROMs, and flash memory. There's not as many types in the logic area that I know of, at least. I'm sure if you ask an actual hardware dev, you'll get lots more information about how they do routing of the various signals, how they write the logic update tables or LUTs. A lot of information that I just don't have. I have never needed that for my job as a network admin, but it's still important to understand what kinds of hardware are there and what it means to you when you have to go update it, and what the risks are and what you need to be paying attention to. So, yeah, there we go. Hopefully you have found this interesting and enlightening just as much as I found it enlightening to look up and read about it when it was new to me as well. Hopefully, hopefully it was an enjoyable little discussion. If you have thoughts on other things that you would like to hear me talk about, or things that you would like to see me demonstrate, feel free to let me know right down there in the comments section. Otherwise, thank you very much for watching. I am your next door net admin, and we will see you next time.